folder number 3. But the land functional analysis 8. No, atam hafta tha kana. Hello. Hello, Rahmatullah. Can you hear me? Hello. Anybody there?
Yes, sir.
Yes, sir.
Right. Welcome. Okay, welcome to this course of functional analysis. This is 8th lecture of the course. And today is Saturday, 2nd January 2021. If you remember, in our previous lecture, we defined isomorphism, isometric isomorphism, and topological isomorphism. Now we shall see applications of these ideas. So far, we were discussing nonlinear spaces of arbitrary dimension. We did not mention anywhere whether our nonlinear space is finite or infinite. From now onward, we shall consider finite dimensional nonlinear spaces because it is very difficult to deal with infinite dimensional nonlinear spaces. If you can see slide, finite dimensional nonlinear spaces, this is the title. And here is one result in finite dimensional nonlinear spaces, which says that any two nonlinear spaces of finite dimension with the same scalar field are isometrically or topologically isomorphic. Means that if we consider two nonlinear spaces x and y of the same finite dimension with the same scalar field, then the two nonlinear spaces are topologically isomorphic. This means that there exists a topological isomorphism from nonlinear space x into the other nonlinear space y. And what is topological isomorphism? If you remember the definition, an isomorphism from nonlinear space to another nonlinear space is a topological isomorphism if there exists T inverse such that T and T inverse are both continuous. When we say that these two topological nonlinear spaces are topologically isomorphic, by definition, this means that there exists a topological isomorphism from nonlinear space x onto the nonlinear space y. Or in other words, you can say that there exists a homeomorphism, or these two topological spaces are homeomorphic. So this is the first result about finite dimensional nonlinear spaces. Let me repeat once again. Any two nonlinear spaces with a finite dimension, remember, a finite dimension with the same scalar field are always topologically isomorphic. We omit the proof because it's too lengthy. If you are interested in the proof of this result, you can see any book on functional analysis. And you can find this theorem under the topic of finite dimensional nonlinear spaces. So it's very important result. It has many applications, as you will see later. Next, we move to another slide. It's a remark on this result. This result says, if we consider any two nonlinear spaces, then by this result, it is clear that they are topologically isomorphic. And if when these two nonlinear spaces are topologically isomorphic, and if one of these spaces is complete, so does the other. Because topological isomorphism, rather isometric isomorphism, satisfies the property of this topological property. And what is topological property? That means if two topological spaces are homeomorphic, means there exists a homeomorphism between them. If one of the topological space possesses some properties, then the same properties will be possessed by the other topological space, and vice versa. This is what we mean by topological property. So this remark says that if for two nonlinear spaces X and Y are topologically isomorphic, and if one of them is complete, so does the other. Now, this is a small result which follows immediately from this previous result. So keep in mind this remark. If two nonlinear spaces are topologically isomorphic, then if one of the nonlinear space is complete, so will be the other. We use this remark in the next theorem. This is theorem says a finite dimensional nonlinear space is complete. A finite dimensional nonlinear space is complete. When you consider any finite dimensional nonlinear space, then it will be complete. And when a space is complete, definition manual equality, if you consider any convergent sequence, this concept is similar to the definition of when a set is closed. By completeness, we mean if every Cauchy sequence is convergent in the space, then this space is complete. So the theorem says that a finite dimension nonlinear space is always complete. It means if you consider any Cauchy sequence in it, by definition, and it is convergent, it will be convergent. But we don't use this definition in the proof. Means we are not going to prove this definition using the completeness definition. We shall prove this result via some other known results. Proof is simple. Just consider two topologically isomorphic nonlinear spaces X and Y, of the same finite dimensional. Then by the above remark, if one of these metric space is complete in the sense of metric space. Yes, complete in the sense of metric, ये हम क्यों बार बार कहते हैं? There is another concept of completeness. When an inner product space is complete. So don't confuse this concept of completeness in nonlinear spaces with that with the orthonormal sets in nonlinear spaces. It has different meaning, this completeness. So in order to distinguish this from the other concept of completeness, we write in the bracket complete in the sense of metric space. Metric space कब complete होता है? When every Cauchy sequence is convergent in it. And you know that हमने एक result prove किया था that every nonlinear space is a metric space. So you can use this concept of completeness in nonlinear spaces as well. Right. So if there is two nonlinear, there is topological isomorphism from one nonlinear space onto another nonlinear space, or they are topologically isomorphic. If this is the case, and if one of them is complete, so will be the other. This is what we stated in the above remark. I just repeated that. Now, consider the space L11. If you remember, when we were discussing nonlinear spaces, we define norm on a linear space, and we said that the pair X and that norm is a nonlinear space. And then we constructed different nonlinear spaces. The first example was that R and C are both nonlinear spaces with the norm defined by X norm is equal to X absolute, where in R and in C, that is in the set of real numbers and in the set of complex numbers. With norm defined in this way on both sets, then they are nonlinear spaces. And then we defined another space LPN, where P was a number greater than equal to 1. And what was LPN? It was your Rn or Cn. That is n-dimensional nonlinear Euclidean space and n-dimensional unitary space. LPN represents these two sets. And we defined two norms on LPN. Now, if you replace LPN represent Rn or Cn, we are considering Rn. Now, if you take, and n varies from 1 to n. If you take n equal to 1, you get the real set of real numbers R. So this L11 is nothing but your R. And you know that this R is complete. So as a consequence of completeness of L11, the finite dimensional nonlinear space L1n is also complete. R, set of real numbers, and its generalization Rn. Similarly, here L11 is your R and L1n is your Rn. In R, you take any element, any number x which belong to R will be any number. And if you take x in Rn, this x will be not just one number, but it is n tuple vector. Means x is equal to x1, x2, x3 up to xn. Means x has n component. So find the difference between L11 and L1n. L11 is your R and L1 is n is your Rn. And we also know that Rn is complete. R is complete, C is complete, Rn is complete, Cn is complete. These are known results. Don't prove it. These are known results. So L1n is also finite dimensional. Dimension here is n dimensional real space, which is complete. And in the beginning, we said that any two nonlinear spaces of the same finite dimension are topologically isomorphic. Now you have this space L1n, which is n-dimensional nonlinear space and is complete. So by the above result, by the above quoted result, if you consider any arbitrary nonlinear space X of finite dimension, then it will be topologically isomorphic to L1n. Your X is n-dimensional nonlinear space. L1n is a finite dimensional nonlinear space of dimension n. So both are finite dimensional nonlinear spaces, and by our previous result, they will be topologically isomorphic. And when two nonlinear spaces are topologically isomorphic, then any property possessed by one space will be also possessed by the other, and vice versa. Here you see that L1n is complete, and it is topologically isomorphic to the arbitrary n-dimensional nonlinear space X. So X will be also complete. And this complete the proof of this result. Hypothesis kya tha? What was the statement of the theorem? Theorem says that a finite dimensional nonlinear space is complete. We considered an arbitrary finite dimensional nonlinear space X, and we showed that this space is topologically isomorphic to L1n because L1n is also n-dimensional nonlinear space, possessing the property that L1n is complete. Since L1n is topologically isomorphic to X, so this property will be also possessed by that arbitrary finite dimensional nonlinear space X. और यही हमने prove करना था. And this proves the result. Now we prove another result. It's similar to this one. This result says if X is a nonlinear space, then every finite dimensional subspace of X is necessarily closed. You see this theorem 1.24 written here, but forget about this number. This is also a result about finite dimension nonlinear spaces. Theorem says if X is a nonlinear space, means it's an arbitrary nonlinear space. We have not mentioned the dimension here, but if we consider a finite dimensional subspace, note this a finite dimensional. If we consider a finite dimensional subspace, say y of X, then this y will be necessarily closed. So by this result, every finite dimensional subspace of a nonlinear space X is always closed. Proof is simple. Consider a nonlinear space X and then consider a finite dimensional subspace y of or m of X. Here we have taken M as a finite dimensional subspace of X. Then this finite dimensional subspace M of X is complete. Why? Because we just proved a result that every finite dimensional subspace is complete. Here your M is a finite dimensional subspace of X, so it will be also complete by the previous result. Now come to recall a result from matrix spaces. If X is a matrix space and Y is a complete subspace of this matrix space, then this complete subspace will be closed. ये हमारे पास matrix spaces में result है. If X is a matrix space and Y is any subspace of this matrix spaces, if Y is closed, then it will be complete. If it is complete, then it will be closed. So by this result, we see that a complete subspace of a matrix space is always closed. So applying this result on M, M is a complete subspace of X. Of X is here nonlinear space, and you know that every nonlinear space is a matrix space. So you can apply this result over here. So by this result, M will be also closed. So it's a simple result. In the first result, we proved that any two nonlinear spaces of finite dimension are topologically isomorphic. In the next result, we proved that every finite dimensional nonlinear space is complete. And in this result, we proved that if M is a complete finite dimensional subspace of nonlinear space X, then it is closed. So remember that every finite dimensional subspace of a nonlinear space is always closed. Up closed, you will be wondering what does this closedness mean? ये already हम define कर चुके हैं. कोई subspace या कोई कब तक closed होता है? Recall your memory. मैंने definition एक जगह लिखवाई थी आपको 4-5. We say that a subspace of a nonlinear space is closed if you consider any convergent sequence in the subspace converging to some limit, and if that limit also belongs to the subspace, then the subspace is closed. Or for that matter, you can say that the set is वहाँ पे हमने सेट लिखा था, but you see subspace is also a set. So this result is true for this subspace. Before proving the next result, we recall one definition from metric spaces. Metric spaces में आपने compactness का concept भी पढ़ा होगा at BSc level and MSc or BS level. But let me recall that definition. We say that a metric space X is said to be compact, not complete. Here we are using this concept of compactness. कोई ना metric space compact कब होता है? By definition, a metric space X is said to be compact or sequentially compact, because we are using this concept of sequence in the definition of compactness of a metric space. By definition, a metric space X is compact if every sequence in X has a convergent subsequence. A metric space is said to be compact if you consider any sequence in X and that has a convergent subsequence, then the metric space will be compact. अगर कोई एक मतलब there are so many sequences in the metric space, if one of those sequences is not compact, then the space is not convergent, then the space is not compact. Definition says if every sequence in the metric space has a convergent subsequence, then the metric space is said to be compact. Now, if we consider any subset M of a metric space X, when this subset will be compact. If you consider any sequence in M and that has a convergent subsequence converging to some limit and that limit also belongs to the subset, then the subset will be compact. अब यहाँ पे थोड़ा सा फर्क है. Metric space कब compact होता है? It is compact if you consider any sequence in the metric space and that has a convergent subsequence, then it is compact. We don't say anything about its limit. But for the subset, definition is the same, but we put one condition on the limit of that convergent subsequence. If that limit also belongs to the set, then the subset is compact. ये याद रखें. सेट का लिमिट सेट के अंदर भी हो सकता है और बाहर भी. So we put this condition on the limit of the sequence, convergent subsequence in M, that must also belong to the subset M. Then the subset will be compact. So mind the difference between complete matrix, compact metric space, and compact subset of a metric space. Metric space is compact if every sequence has a convergent subsequence. That's it. And when a subset of a metric space will be compact if every sequence has a convergent subsequence, provided that the limit of the subsequence also belong to the subset. Right, now we recall one theorem from metric spaces. You don't need to prove these results. We are recalling simply to refresh your memory. और इन रिजल्ट को हमने आगे यूज करने हैं अपने नॉन लीनियर स्पेसिस के मुताबिक जितने भी रिजल्ट्स है. There is one important result in metric spaces, and that result is called continuous mapping. If it is any map from one metric space into another metric space, then we say that and if this mapping is continuous, T is a continuous map from a metric space X into another metric space Y. And if you consider any compact subset M in X, that is in the domain space, and the image of this compact subset under this continuous map T will be compact in Y. This is what the continuous mapping theorem says. It says that if it is a continuous mapping from a metric space X into a metric space Y, and if you consider any compact subset in the domain space X, say M, then the image of M under this map T, that is Tm, that will be compact in Y. So this is the continuous mapping theorem in metric spaces. Now using these concepts, we prove this theorem. Theorem, yes. Theorem says, this theorem 1.27 is here written, but as I said, forget about the number because I have omitted some of the results. The theorem says if X is a finite dimensional nonlinear space, then each closed and bounded set in X is compact. एक तो आपके पास definition है, when a subset of a metric space is compact, and now you have this result. If X is a finite dimensional nonlinear space, then each closed and bounded set in X is compact. ये जरा ख्याल रखें, we are not considering an arbitrary nonlinear space, we are considering finite dimensional nonlinear space. Then each closed and bounded set in this finite dimensional nonlinear space X is always compact. As I said, we prove this result with the help of our previous known results. First, consider an n-dimensional nonlinear space X. That is, this X is finite dimensional nonlinear space whose dimension is n. Next, consider a closed and bounded set in this finite dimensional nonlinear space X. And we say that this closed bounded set is M. अब करना क्या है? We have to prove that this closed and bounded set M in X is compact. Right? X is n-dimensional nonlinear space. M is a closed and bounded set in X. We have to prove that this. Hello? Sorry? Right. Please move to your mic. We have to prove that this M is compact in X. We recall our previous result, which says that any two nonlinear spaces of the same finite dimension with the same scalar field are topologically isomorphic. ये finite dimension nonlinear spaces का पहले वाला result था, which we stated only without proof. So here we are recalling that result. So there exists a topological isomorphism from this finite dimensional nonlinear space X onto the finite dimension nonlinear space L1n, because L1n is also a finite dimensional nonlinear space of dimension n. Both X, by our assumption, is a finite dimensional nonlinear space, and we know that L1n is a finite dimensional nonlinear space. We have to prove we know that these two n-dimensional nonlinear spaces are topologically isomorphic. So we say that there exists a topological isomorphism T from X onto L1n. This is by our previous result. Right. Now consider any closed subspace, closed and bounded subset M in X, and T is a topological isomorphism, means that T is continuous. So the image of M under this T will be an element of Y, which is your space L1n. So this Tm will be compact in Y. We have denoted Tm for simplicity's sake by K, or in other words, K will be compact in L1n. And this will be also bounded. Why? Because we have one result in real analysis which says that each closed and bounded set in L1n is always compact. Let me repeat once again. T is a topological isomorphism from X onto L1n. So by this topological isomorphism, T is continuous. Topological isomorphism की definition क्या है? When T and its inverse are both continuous, and T is a isomorphism, then it is called topological isomorphism. Not using your result that the image of this closed subspace M under T will be closed and bounded in L1 n means K is compact. Why? Because we have a result in real analysis which says that L1n क्या it's your space Rn, which says that each closed and bounded set in L1 is always compact. By this result, Tm, which we have denoted by K in Y, will be compact. Next, since T inverse exists and it is continuous by topological isomorphism, because T is a topological isomorphism. So T inverse exists and it will be a map from L1n to X. T was a map from X to L1n. Its inverse T inverse will be a map from L1n to X. And this T inverse is continuous. Now using your continuous mapping theorem, T inverse is a map from L1n to X, and T inverse is continuous. And continuous mapping theorem says that the image of any compact set in the domain space under this continuous map is compact in the range space. Now here your domain space is L1n and your range space is X, and Tm was a compact set in L1n. So the image of this compact set, that is Tm under this T inverse, will be compact in X. Now T inverse and Tm, this implies T into T inverse is equal to identity map Im, which is your M. So this, the image of Tm in L1n under this continuous map T inverse will be an element of X, and T inverse T is equal to Im, which is equal to M. So M is continuous in this space L1, sorry, in X. और ये हमने प्रूव करना था that M is, which is a finite dimensional closed linear subspace, closed and bounded set in X is compact, and this completes the proof. So it was a little bit about finite dimensional nonlinear spaces. Remember that the converse of this result is also true, which is obvious. Anyway, I have put the details here over here. The converse of this result says if X is finite dimensional nonlinear space, then each compact subset M of X is closed and bounded. Sorry. In the main result, we proved that if X is a finite dimensional nonlinear space, then each closed and bounded set in X is compact. Now we consider a compact subset in this X, and we have to show that it is bounded, closed and bounded. Proof is obvious. Why? Because we know that each compact set in a matrix space is closed and bounded. अब X क्या है? X is your nonlinear space, which is by one of our previous result is a matrix space. So if we consider M as a compact set in X, then by this quoted result, it must be closed and bounded. So this converse of this result is obvious from the known result in matrix spaces. Right now we can combine these two results. That is the first result, which says that if X is a finite dimensional nonlinear space, then each closed and bounded set in X is compact. And by this result, if X is a finite dimensional nonlinear space, then each subset M of X is closed and bounded. So you may combine these two results. And you have the following statement. In any finite dimensional nonlinear space X, any subset M of X is compact if and only if M is closed and bounded. If the question is in this form, in the examination paper, then you have to prove, write the proof of both way. That is, first you have to consider M finite dimensional nonlinear space and M as a compact subset of X, and you have to prove that M is closed and converse, compact, bounded, and then the converse means consider M as a closed and bounded subset of this finite dimensional X and prove that M is compact. So this was some results about finite dimensional nonlinear spaces. Now we prove this last result of midterm course. The last result is this F. Rees lemma. F. Rees lemma. This lemma says, try to understand the hypothesis. It says that Y be a subspace of a nonlinear space X. You see in the bracket, we have written that of any dimension, finite or infinite, but Y is a subspace of this nonlinear space X, such that the subspace Y is closed and a proper subset of X. X is any finite dimensional nonlinear space, Y is a closed and proper subset of X. This is the condition on Y. Next, we have to prove that for any real number theta in the open interval 0, 1, theta belongs to this open interval 0, 1, it is greater than 0 but less than 1. Endpoints cannot be the values of theta because theta is greater than 0 but less than 1. You can take this as any rational number. Then we have to prove that there exists a vector x in the nonlinear space X such that the norm of this vector x is 1, and for any other point y in y, xy minus y norm is always greater than this theta, which is a number in the open interval 0, 1. Let me repeat once again. X is any nonlinear space. Y is a closed and proper subset of X. Then we can find, then for any, if you consider any theta in the open interval 0, 1, for this theta, there exists a vector x in X such that its norm is 1, and for any other element y in this x, the norm of x minus y is greater than this number theta. This obviously this theta will be a rational number because it belongs to 0, 1. Can be 1 over 2, 1 over 3, 1 over 4, and so on. Proof. Now look at this figure. This is your x, your nonlinear space x. Y is a proper closed subset of x. Proper means that every element of this set must belong to x. And this subset is also closed. Means the boundary points are included in this set Y. Right. We consider a point in the complement of Y. It does not belong to Y. It is in the complement of Y, this point P. And denote its distance. Denote the distance of this point P from the proper closed subspace Y of X. So by definition, this D will be equal to infimum P minus Y now, where this Y belongs to Y. This is the definition of distance. Distance is the smallest path from P to Y. If your Y is here, this is P, then this is not the distance. Distance is the smallest one. Distances आपके पास बहुत सारे होते हैं, उनमें जो smallest होगा, that will be your distance. So this is by definition of distance, D will be equal to infimum taken over x minus P minus Y now, where this Y belongs to Y. Now you see D is a distance. So clearly this D is greater than 0. And you see this P cannot coincide with Y. P और D coincide नहीं कर सकते because P is in the complement of Y and Y is closed. ये P Y के साथ coincide नहीं कर सकता because it's in the complement. And furthermore, this P is closed. और ये Y यहाँ से बाहर नहीं जा सकता. It's the boundary of this Y, and Y, since Y is closed. And next, consider any number theta in the open interval 0, 1. By definition of infimum, there is another point. There is a point Y naught in the closed subspace Y such that P minus Y naught now, consider P minus Y naught, this is your P, which is in the complement of Y, and Y is inside this Y. So P Y now, this will be greater than D. Why? Because D is the infimum taken over P minus Y norm, where Y is any element in this Y. Right? D is the infimum, and P minus Y naught is not the infimum distance. It's any distance of P from Y naught. So this p minus y naught norm will be greater than d and less than equal to d divided by theta. D is less, but this is less than d over theta. It looks a bit awkward, but you see theta is a rational number, that is 1 over t. So this d divided, for example, if you take theta equal to 1 over 2, then this is less than d divided by theta will be equal to d divided by 1 over 2 theta, which will be equal to 2d. And this term in the middle, that is p minus y naught norm, is greater than equal to d, but will be less than equal to 2d. So this, don't be confused. The d is less than equal to p minus y naught, but it is less than equal to d divided by theta. अगर थीटा आपका कोई नंबर होता 2, फिर तो ठीक था, गलत था, then it is not possible that this norm is less than equal to d divided by 2. But since theta is a rational number, 1 over 2, which is equal to 2d, so this we have this inequality, d is less than equal to infimum of p minus y naught norm less than equal to 2d. Anyway, denote this by 1. Now construct a vector x as c into p minus y naught. Your x is equal to c into p minus y naught, where this c is any constant that is 1 divided by p minus y naught norm. You see that norm is a real number. So this is any positive real number. Now look here, this x is equal to c into p minus y naught. X is your linear space. So this x, which is equal to c times p minus y naught also belong to x, since x is a linear space. Linear space क्या होता है? Linear space is closed under addition and scalar multiplication. ये scalar multiplication है. This is scalar and these are elements of the linear space. So this c times constant time p minus y naught belong to x, since x is a linear space. And norm of this x is equal to 1, means the vector we constructed is a unit vector. दोनों साइड का नाम ले लें and you will get that this right hand side is equal to 1. यहाँ पे आपके पास नाम आ जाएगा c into p minus y नाम, but your p is c is equal to 1 over p minus y naught नाम. So p minus y naught नाम cancels with p minus y naught नाम. If you put the value of c here and then take norm of x, you get 1. So we found a vector in x whose norm is 1. It remains to prove that एक कंडीशन ये थी आपकी स्टेटमेंट की कि आपने प्रूव करना है देयर एग्जिस्ट ए यूनिट वेक्टर इन x. वो तो हमने फाइंड कर लिया. We found such a vector whose norm is 1 in x. अब प्रूव क्या करना है? We have to prove that its distance from any other point in y capital Y, that is the closed proper subset of X, is always greater than this number theta, which is in the open interval 0, 1. Now to prove this, X minus Y norm is greater than theta, we start with considering X minus Y norm, which can be written as your X is C times P minus Y naught minus Y norm, putting the value of X here, and then using the properties of a norm, you can take this constant C outside, and inside you are left with P minus Y naught minus C inverse Y, and this can be written as C times P minus Y naught plus C inverse Y, and this can be written as C times P minus Y1. What is this Y1? This Y1 is equal to Y naught plus C inverse Y. Then this new vector Y1, which is equal to Y naught plus C inverse Y, this belongs to Y. Why? Because Y naught belong to Y, Y belong to Y, Y is a subspace, so this C inverse Y also belong to Y, and then Y naught plus C inverse Y, that is this sum of two vectors of Y belong to Y, because Y is a subspace. Y set nahi hai. In the hypothesis, if you see that Y is a subspace closed and proper of X. So this vector Y1 constructed in this way belong to Y. Then this distance of Y1 from P will be greater than D, क्योंकि ये Y1 हमारे पास कोई और वेक्टर आ गया inside Y, so the norm of that P from Y1 will be greater than D. D is your infimum taken over P minus Y, where Y belong to Y. And then X minus Y norm can be written as you see above, which is equal to C times P minus Y norm, and this P minus Y norm will be greater than C into D, because P minus Y norm is greater than D, but your C is 1 over P minus Y norm into D. This is by equation 2, and this can be written as D divided by D theta, because P minus Y naught norm is less than D over theta, and this can be written as, after simplifying the above, you get theta. So you get X minus Y norm theta greater than X minus Y norm greater than theta, and this completes the proof, because you found a vector X whose norm is 1, and X minus Y norm is greater than theta for any Y in Y, and this was required, and this completes the proof. So this was the last result of this midterm course of functional analysis. So remember that the paper will contain questions, what we have studied till date. So please try to prepare this whole course for the midterm exam. And also remember that you have to upload your first assignment by 10th of January. So don't forget the assignment as well. So this was all about today's lecture. No any question? No question? Hello?
Yes, sir.
Okay, don't go away. We will start the other lecture soon, right?
Okay, sir. Thank you.
Okay. One, two, three, four, five. So out of 24, only 5 are present.
Yes, sir.
Right, it's not good. Okay, anyway, see you in a moment.